So I just want to see if, yeah, now I'm recording. Okay, so team, we come to this tutorial, which is tutorial number 2 and the last tutorial for this module. Also, guys, I'm sure you know the ground rules. Make sure that your mic is on mute, and also you turn off your camera. Make sure that your camera is off and you are always on mute. If you want to say something or if you want to contribute, just raise your hand. I spot you. If I failed to, you can actually unmute yourself and interrupt. It's okay. Thank you for that. I'm sure you are seeing my screen now, and we are going to do the sequences and the strings. That's where you are going to start. Sequences and string. That's the topic there. Okay. Let me just also pick my highlighter. This one, the green one. Okay. So by the end of this unit, you should be able to first describe the concept of sequences and operations on sequences. Also discuss the concept of strings and operations on strings as well. So I'm not going to waste much of our time on this topic. I'm sure it's very easy to comprehend. I'm sure to all those who have actually come through this topic, I'm sure you understand that it is not, there's no much difficult in this topic. So the definition for sequences, for a sequence, the definition for a sequence whose smallest index is 1 is a function whose domain is either the set of all positive integers or a set of the form 1 up to what? Up to n. So a sequence whose smallest index is 1 is a function whose domain is either the set of all positive integers or a set of the form 1 up to n. We are saying if you've got a sequence which starts or its smallest number is 1, it means it's a sequence which contains positive integers. It is actually starting from 1 up to n. So if S is a sequence, we denote the first element as S1. As S1, just S1. The one is just like a subscript there. So if if S is a sequence, we denote the first element as S1, the second element as S2, which is something like S with a subscript 2 and so on. So you can have S1, S2, S3 up to Sn, where S1 refers to the first element in your sequence. So in general, Sn denotes the nth element. When you are talking about Sn, it will be the nth element of the sequence. So the nth element, the n there, it will be just a variable which will be waiting for an index so that you can substitute an index and then you can take the value at a specific index. Maybe the 50th term, so you end up having S5. Maybe if it is the 6th, you have S6. So this n is just a general term. So the ordered list 2, 4, 6 up to 2n is a sequence. The first element is 2, the second element is 4, and so on. The nth element is 2n. If we let S denote this sequence, we have S1 as 2, S2 as 4. This one is our S1, and this one is our S2, and then S3, which is equal to what? Equal to 6. And the Sn, which is the general formula now, which gives us all the values within the sequence or all the terms within the sequence, which is 2n. If you want the first element, which is S1, you can say 2 times 1, and then you can get your 2 there. If you want the second element, you can say S2, which will give you 2 times 2, which is going to give you a 4. If you want S3, you can put here 3 here, and then you have 2 times 3, and you can get S6, which is S3. So this Sn is just a general formula which will give you the nth term of your sequence. The nth term of a sequence. And then we can have this one is just an example on how you can use sequences. So Munenza buses charges $1 for the first kilometer, So for every kilometer, then they charge what, 50 cents for each additional kilometer. So for the first kilometer is just $1. Then for every additional 1 kilometer, you are going to incur a 50 cents charge instead of $1. So in general, the cost CN of traveling any kilometers is $1. The cost of traveling the first kilometer plus 50 cents times the number, which is n minus 1 of additional kilometers. That is, you end up having this formula which you generate the cost of n kilometers. Maybe if you are traveling 20 kilometers, you know that for the first kilometer it's $1, and then for the 19 kilometers now you say 0.5, which is the 50 cents times 19, and then you add to $1, you get the total. So here we are putting n minus 1 so that we subtract the first kilometer from n. So if you are saying the n there is going to be 20, which means you are traveling for 20 kilometers, it would be 20 minus 1, and then you get what? You get a 19 times 0.5, then plus 1. That's how you can use some sequence. So this one is it's an n-th term. So this one is a general term which actually produces the whole sequence. That's like that. So this one was when you travel 1 kilometer, is it 1 kilometer? For example, this one is n minus 1. 1 minus 1 is going to give you a 0. So, okay, this one we travel 1 kilometer. Then this one is when you travel 5 kilometers, which is going to give you $3 is what is cost. So the list of fares in the example above is in sequence. A sequence can have repetitions as well. A sequence can have repetitions as well. Okay, so let's look at the types of sequence. We also have the types of sequence, which are the decreasing and increasing sequence. So if it is decreasing sequence, we are saying you are starting from the higher value just going down. That's the decreasing sequence. Maybe from positive going to the negative side, that's the decreasing sequence. And then if it is an increasing sequence, it means the first term is smaller than the second term. So in other words, as you go up the sequence, the values or the elements gets high, just like that. So definition, a sequence is increasing if Sn is less than or equal to Sn plus 1. So in other words, if the previous element is less than or equal to the second element, it means that that sequence is what? Is an increasing sequence. That sequence is an increasing sequence. So it's as good as here we have a 1, and then we have a 2, and we have a 3. So this one is always less than or equal to this one, and this one is always less than or equal to this one. So it's an increasing one. It's an increasing sequence. So the sequence 2, 4, 6 is an what? Is an increasing sequence, just like that. It is an increasing sequence. So I want to add people lobbying. Okay. So that's what you call an increasing sequence. That's what you call an increasing sequence. So it's just the same with a decreasing sequence. On a decreasing sequence, this one is whenever you have Sn is greater than or equal to Sn plus 1 for all of n. So in other words, it's the reverse of this one or the opposite of this one. When you have the values which are decreasing, so Sn or the previous value is always greater than the what? It's always greater than or equal to the next value. That's what you call a decreasing sequence, a decreasing sequence. So maybe you might have 2, 1, 0, minus 1 just going down. That one, it will be a decreasing one. It will be a decreasing sequence. Let's talk about a subsequence. You can also have a subsequence, which is the part of a sequence, but not the whole sequence. Right? If the sequence is 2, 4, 6, 8, you can have 4, 6 as the subsequence, which is the part of the sequence, but it's only that which is the sequence as well, but it's just the part of the sequence, not the whole sequence. So let Sn be a sequence defined for n is equals to m, then m plus 1 up to and let n1 and n1 n2 be an increasing sequence satisfying nk, then nk plus 1 for all k whose values are in the set. So this one is just some definition there. This one is just some definition. But in general, the sequence BC is a subsequence of the sequence AABCQ. So you are saying we have this sequence with these terms AABCQ. So you can have this BC, you can have this BC. Now this BC is a what? Is a subsequence. You can have that BC as a what? As a subsequence, just like that. So notice that the sequence CB is not a subsequence of the sequence. If you are going to take CB, this one, it's not a, it will be not a what? It will be not a subsequence because we do not have a CB there. What we have is a BC. So the order is very important for subsequence. So the sequence 2, 4, 8, 16 is a subsequence of the sequence 2, 4, 6, 8, 10, 12, 14, 16. So you can even jump some of the values, but you cannot reverse them on the subsequence. That you cannot reverse them. You cannot reverse. And then let's look at the sequence operation. The sequence operation. So if AI from I to n is equal to m is a subsequence, and then we define the sum and the product of terms in the sequence S. In other words, you can find the sum. You can find, sorry, I'm just trying to add some people here. So you can find the summation or the multiplication, or we call it the projection of the multiplication of what? Of subsequences. You can find the multiplication or the summation of subsequences. How can you do so? You can actually add from from I is equals to m up to what? Up to n. Can do the summation, which is am plus 1 plus dot up to an. You can do the same if you are multiplying. You can multiply am times the am plus 1 times an. So in other words, if it is a sequence of 2, 4, 6, 8, just multiply 2 times 4 times 6 times 8. If it is the addition, 2 plus 4 plus 6 plus 8, just like that. So this one is just an example. Let's let a sequence be defined by an, which is a with a subscript n, be equal to what? To 2n, where n is greater than or equal to 1. Take note of this one. Your n is always greater than or equal to 1. So greater than or equal to 1. In other words, your sequence is starting at what? At 2 as the first element. Because you're going to put 1 here, it is going to give you 2 times 1, and then you get a 2 there. So the first element is 2. The second element, it will be 2 times 2 is 4. So it's just the multiples of 2. Starting from 2. So it will be 2, 4, 6, 8 up to n. So here we are looking for the summation from n is equal to 1 up to n is equal to 3. So because here we are starting at I is equal to 1 up to I is equal to 3. The summation from I is equal to 1 up to I is equal to 3. So AI will be equal to A1 plus A2 plus A3. That's what we are supposed to do there. So it's a subsequence of the whole sequence. So you'll be adding 2 plus 4 plus 6, which will give you a 12 there. If you are going to do the multiplication, you do the multiplication of A1 times A2 times A3, which is going to give you this 48. So this one was also an example 2, but this one I'm sure you can just do this one as well. It's very simple. Not want to waste time on this one. Let's talk about the arithmetic progression. This one is also a sequence, but it's a special type sequence. It's also a sequence, but it's a special type one. Trying to add someone in the loop, but don't know what's happening with their network. Okay, so this one, arithmetic progression, is a special type sequence which follows some rules, which follows some order there, And normally, if you want to see if a sequence is an arithmetic progression, it must have what we call the common difference. It must have what we call the common difference, where the subtraction of the element a plus 1 and the element at a will always be the same when you are subtracting the one at a plus 2 with the one at a plus 1. So in other words, the second element from the first element and the fourth element, maybe from the third element, the difference there must be the same. That's what we call the common difference. So if you have such behavior where you can pick maybe two elements and define their difference and go and pick any other elements, any other two elements which are consecutive elements, or talk of consecutive elements, and you subtract them, you always get the same number. It means that sequence is an arithmetic progression. So here are some of the formulas that you can take note of. There is sum of first any terms of an arithmetic progression. If you want to find the sum to n, or sum of n elements in an arithmetic progression, you can use Sn is equals to n over 2 multiplied by 2a, where a is the first element in your arithmetic progression, or this a is always the first term in your arithmetic progression, plus n minus 1 times d, which is the common difference. So for you to find the sum to n, maybe you want to sum, just like here, we're supposed to find the sum to 3, which means we want to sum the first 3 elements. So here maybe we want to sum the first 20 elements there. What you need is the common difference as well as the first element. By having these two things, you can have the sum to 20 or the sum to n terms. If Sn is sum of any terms of an AP, whose first term is A and last term is L, then you can also use n over 2 times A plus L. In other words, you can also have, sometimes you can be given the last term and the first term, and you'll be asked to find the sum to n. You can use this formula where you do not have this d, the common difference. You might not be given the common difference. You can use this formula, the sum to n. Maybe you'll be given this n and this a and this l, which will be the last term. So if common difference is the number of terms n and the last term l, then you can also use this formula. In other words, you do not have an a there, you can also use this formula. So these are some of the formulas that you can use there, Okay, also there's this formula of the nth term of an arithmetic progression. Maybe you are given maybe 2, 4, 6, and you'll be asked to find maybe the fourth element or the fourth term of this AP, because this one's an AP. If I say 4 minus 2, I will get a 2. And if I say 6 minus 4, I will always get a 2. So since the common difference is 2, so this D will be equal to 2. The common difference will be equal to what? Will be equal to 2. That's our common difference. So since the common difference is always equal to 2, so you can also use this formula to find the fourth element or the fourth term of this AP, of this arithmetic progression. How do you do so? you need to have an A and you need to have an and you need to have this D, and then you solve for this N. You solve for that N, just like that. So here I want, you notice so for this N is 4 because we just want to find the fourth element. So it will be 4 minus 1 there. So you just do the substitution. So your A will be equal to 2 because remember A is the first element of this AP. So it will be just like 2 plus 4 minus 1. So I'm using a mouse to write. Let us not a touch screen. So yeah, expect much more of this. All right, and then this D is what is 2. The common difference is what is 2. So it will be 2 plus 4 minus 1 is 3. 3 times 2, you get a 6. So it will be 2 plus 6, which is equal to 8. So in other words, the fourth term is what is 8. And if you look at it, it's 2, 4, 6, 8, which is actually true. So you can use this formula to find the nth term of an arithmetic progression. So sum the series 2 plus 4 plus 6 up to 4 terms. You can use the formula, which is this formula. You can use this formula to find the summation up to 40 of such elements. So in other words, if you look at this one, it's just 2, 4, 6. So the common difference is 2, and then your A is 2, and then you are asking to find the summation up to 40. So you can use this formula where you have your A, you have your D, and you have your N. Then you can just substitute. Your N is 40 because we want the sum to the 40th term. So from the first term until we reach the fourth, the 40th term, and then find the sum of the first 19 terms of the AP, whose n in the term is 2n plus 1. So you've given this n in the term. So this one is the one which we are going to use to generate the elements or the terms of this AP, and then you'll be asked to find the term at the number 19 or the 19 in the term of this arithmetic progression, and you are being told that this is an arithmetic progression. Also this one, find the sum of the series 1 plus 3 plus 5 plus dot dot up to 99. So in other words, you are being given that this series actually you want to find the sum from the first term to the 99th term. I don't know, is it the 99th term? I don't think so. I think with the common difference there are some of the something that we need to work there. So this one, we see that given series is an arithmetic progression with first term A is equal to 2. So this is this one. Okay, so our A is 2, and then the common difference 6 minus 4 is 2, and 4 minus 2 is 2. So the common difference is 2. And then here N is equal to 40. So here our A is equal to 2. And then our D now is equal to 2 as well. And then our N is what? Is 40. Our N is 40. And remember, the formula was just as this one, N over 2 times everything here. So you can have, that's why we are having this N and then over 2 here. We're dividing everything by 2. So you can have N over 2 here, or you can just say N multiply this one and then divide everything by 2. So if you look at this one, you're going to have 2 times 2, which is going to be a 4, and then 40 minus 1 times 2, which is going to give you maybe something like this, and then 20 times 4. Okay, in other words, we have divided this 2 into 40, and then you get this 20, and then this one gets 78. If you multiply 39 by 2, you get 78, and then 84 there, and then you multiply it by 20. That's how you get this one. So this one is the summation of the first 40 terms of this arithmetic progression. So first term A, which is was T1, what we were finding here. Find the sum of the first 19 terms of the AP, whose nth term is 2n plus 1. So the first term, which is T1, you can only have the first term whenever you put 1 there. So it will become 2 times 1 plus 1, which is going to give you 3. So our A is equal to 3, right? And then since you have your A there, if you want to find the nth term, if you want to find the nth term, what do you do? If you want to find the nth term, what do you do there? You are given here 19. Find the sum of the first 19. Okay, you want to find the terms of the sum from the first term to the 19. That's what we want to do there. So maybe we want another term there. What else? Okay, here they find the last term, which is at the 19. Then they want to use the formula. Which one? This one. This formula. They want to use the formula where you have n over 2 times a plus 1. So they have actually find this first term, and then they are finding this one. So it's up to you. You can actually find maybe 3 consecutive numbers, and then you find the common difference there, and then you find maybe you have your a as well as the n, which is 19, and then you can calculate the sum to n. You can always have your answer there, or you can just find the first term and the last term, and then you can use this formula, this one, n over 2 times a plus l. This is the formula which we're being used here. So the last term was the 19 in the term, and then which was 39, and then the first one is 3. So you're going to use n times a plus l over 2, which is going to give you 19 times 3 plus 39 all over 2, which is going to give this one, just like that. And then problems for practice in an arithmetic progression. The fourth term is 14 and the sixth term is 20. Find the first term and the common difference. Find also the 70th term. I'm sure this one, you can do this one. What can you use here? What can you use? You are told that the fourth term is 14 and the sixth term is 20. So I'm sure you know the formula to find the nth term of an arithmetic progression, to find the nth term of an arithmetic progression. So what you just need is to substitute. What you just need is to substitute what you have been given. Your n is 4, and the answer that you must get for that term is 14. In other words, the fourth term is 14. And then the sixth term is what? Is 20. So if you come here, where do we have the formula? This one, the nth term. Let me wrap everything. Okay. So if you look at this one, an, which is our maybe fourth term, is what? Our fourth term is 14. So our fourth term is 14, just like that. Our fourth term is 14. So maybe you can have 14 is equal to a plus the fourth term. So it will be 4 minus 1 times d, which is the common difference that we do not have. So end up having 14 is equal to a plus 3d. So if you look at this one, you have the sixth term as 20. So you can also have your 20 here is equal to, remember, it's a plus n minus 1, which is we want the what? The sixth element. So it will be 6 minus 1, which is going to give us 5d. So whenever you have something like this, I'm sure it's not new in the world of mathematics. This one, it's not new. You have 2 equations, which means you have simultaneous equations that you can solve. You can use substitution, you can use elimination method. I'm sure here there is no any excuse, because this one is an O-level stuff, not A-level stuff. So I'm sure there are no excuse. What you can do by elimination, I'm sure it's the simple one to use here. Since we have the coefficient of a as the same, you can subtract the equation 1 from equation 2. You can say 5, maybe 20 minus 14, you get a what? You get a 6, b equal to a minus 8, 0. 5d minus 3d, you can get a 2d here. Then if you divide by 2, you can get your common difference as what? As 3. That's your D. The next thing is to find an A. So what you do, you can substitute in any of these equations. So you can put 3 maybe on this one. If you put 3 here, it will be 3 times 3, then you get a 9. And then 14 minus 9, it's 5. So your A there is what? Is equal to 5. And then the next thing that you were being asked to do was to find the 17th term. So the 17th term, you know that the formula is here, AN is equal to A plus N minus 1 times D. And then you have your A, you have your D, and you have your N here. Your N is 17 plus 1, the 17th term. So it will be actually 5 plus 16 times 3. That's your what? That's your 17th term. Just as simple as that. Do I have some questions on the arithmetic progression? Do I have some questions on the arithmetic progression or some contributions? Okay, so if I do not have questions here, the task that I'm going to give you is to go as well and have some look on a geometric progression. I didn't include it here. You can also do it, you can read it on your spare time on the geometric progression. There are some formulas there, and there's common ratio instead of common difference, and then you can do the mathematics. There are some simple formulas which were there that you can actually, which are there that you can follow there. So let's talk about strings so that we can finish off this. Can we make sure that all our mic are on mute if you are not going to contribute or to ask some questions? Thank you. So definition of a string over X is a finite sequence of elements from what? From this X. So let X be a set with A, B, C. If we let Q1 be equal to B and Q2 be equal to A and Q3 be equal to A and the Q4 be equal to C, we obtain a string over X. This string is written BACC. BACC. This one, you can say this is a string over the set X because the elements that we have in this string, they are coming from the set X. So it's a string over what? Over X. Also, we let X star denotes the string of all strings over what? Over X. This one will be representing all the strings over what? Over X, including the now string, and we let X plus denotes the set of all non-now strings of what? Of X. This one will be actually represent all the strings which are not now non-now strings. So the string with no elements is called the now string. If there are no elements, it's a now string. I'm sure you have seen this from other programming languages when you are trying to come up with a string and then you want to display it, but you didn't actually initialize it. Normally to have a now value because there's nothing there. And it's denoted by, or it's denoted as this symbol. I'm sure it's lambda, this symbol, in an empty string or a now string. So let X be the set with A, B, some elements in X star lambda itself, A, B, A, and B itself, as well as A, B, B to the power 20, which means of what? B, which are 20 there, and then A to the power 5, BA, something like that. These are some of the elements or some of the strings that we can have from this set. Not that these are not all the elements that all of the strings that we can have. And then also for this definition, which says the length of a string, which is represented by this alpha, is the number of elements in that string. So the length of alpha is denoted by the modulus of alpha, just like that. The modulus of alpha, just like that. So if alpha is equal to AAB and AB, and the beta is equal to this one, then the modulus of alpha here, or the length, is 5. How do we get to 5? You just count 1, 2, 3, 4, 5. As well as here is 39. How do we get 39 there? 32 plus 4, 36 plus 3, you get a 39 there. So in other words, a cubed, you are saying this is just a list of A, where we have 3 A's, and then B to the power 4, we have 4 B's, and then we have 32 A's. If you add all of them, you get 39. So in other words, the alpha there is just the modulus of alpha is just the length of the string. So if alpha and beta are two strings, the strings of alpha followed by beta, written as alpha beta, is called the concatenation of alpha and beta. There's what we call string concatenation. I'm sure from your C programming knowledge, you know that you can do string concatenation where you'll be joining two strings. So if T is equals to AAB and E is equals to CABD, then TE, in other words, TE, you are joining T and E, and also take a note of the order, it's TE. So it will be AAB and then CABD. We are just appending this one at the end of this. If it is ET, it's just vice versa. We are taking this T and put it at the end of E. And then if it is T lambda, you know that this one, lambda, is an empty string. It's a null string, so it will just remain the same. So in other words, T lambda is always equal to T, or lambda T is always equal to T, just like that. That's all on the strings. Do I have questions or contributions before I move to the next topic? Do I have questions or contributions before I move to the next topic? Okay, so if I do not have questions and contribution, I'm not going to ask you anything on this one. Let me share. Let me share the slide for the next topic, which is the propositional logic. Let's do the propositional logic, which is a long one, I'm sure you have done something on this one. Have you done propositional logic before? When I'm saying before, I'm not saying maybe in your A level or O level, but I'm saying before attending this tutorial.
No, we haven't, sir. Oh, personally, I haven't.
Okay, though it was, I'm sure it was part of your assignments, but anyway, it's okay. I know most of you just give the assignments to some people and then they just write for you. Yeah, I know it happens a lot. It happens a lot, but it's also good to make sure that you do your assignments alone. It will help you also in the exam. Okay. Make sure that you revise your assignments as well. Okay. So let's talk about propositional logic. Let's talk about the propositional logic. So by the end of this unit, you should be able to explain the concept of propositions, apply operations on a propositional on the propositions by using truth tables. You need to also be able to understand how you can use truth tables. So introduction: in developing a mathematical theory, assertions or statements are made. Assertions or statements are made. These statements are made in the form of sentences using words and mathematical symbols. When proving a theory, a mathematician uses a system of what? Of logic, where you say this one can imply this, or this one can give us this, so that you can assert this one is true. So this is also the case when developing an algorithm for a program or a system of programs in a computer science. The system of logic is applied to decide if a statement follows from or is a logical consequence of or one or more other statements. So let's talk about the logic. So logic is the study of principles and methods that distinguishes between a valid and an invalid argument. So in other words, you need to be able to distinguish a valid argument, and an invalid argument. So logic is the basis of all mathematical reasoning and of all automated reasoning. When you said I've proved this, that this is correct, you are using logic. You are using a series of steps. That's what we call logic. So it is practical implications, or applications to the design of computing machines, to the specification of systems, to artificial intelligence, to computer programming, to programming languages, and to other areas of computer science, as well as to many other fields of study. I'm sure you can always test if this one is true, then do this one. It's always logic. It's always logic. Okay, so let's talk about what we call a statement. What we call a statement in propositional logic. What we call a statement. So a statement is an assertion or a declarative sentence that is either true or false, but not both. So what we call a statement is just an assertion or a sentence. But that assertion or that sentence, it must have a truth value of either true or false, but it cannot be both. And then we can say that this one is a what? Is a statement. Otherwise, a statement is also referred to as a what? As a proposition. We can call it a proposition. Otherwise, if it is not going to have a truth value of true or false, then it's not a statement or it's not a proposition. So when you are referring to a statement, it's as good as referring to what? To a proposition. So they can be used interchangeably, proposition or a statement. So the truth value of a mathematical statement can be determined by application of known rules, axioms, and laws of mathematics. So a statement which is true requires a proof. For you to say this statement is true, you need a proof that this statement is true. For example, 2 plus 2 is equal to 4. You need a proof. It is Sunday today. You need a proof. Is it today a Sunday? No, it's not a Sunday. So the statement is what? Is false. Is 2 plus 2 is equal to 4? Yes. Hence, the statement is what? Is true. And then we can call this one as a what? As a statement. So it means this one is a statement, this one is a statement, because it has got a truth value of either true or false. So if a proposition is true, its truth value is true. If a proposition is false, its truth value is what? Is false. So the truth values true and false are respectively denoted by the letters T and F, or by 1 and 0 respective. So you can use, for true you can use T, for false you can use F. You can also use a 1 for true or a 0 for false. Just take note of that. Let's look at the symbol statement. So we are from the statement, and then now we are looking at the what we call a symbol statement. So there's a symbol statement as well as a compound statement. So a symbol statement or a primitive statement is a statement which cannot be broken down into anything simple. So in other words, it is already in its simple terms. That's why we call it a symbol statement. So a symbol statement is denoted by use of letters P, Q, and R. Normally here, we normally use the letters P, Q, and R. P, Q, and R. You are free to use any of the letters that you want. But normally for simple statement, we normally use these small letters P, Q, and R to denote our statements. And normally it is written that P is such that, or the statement P is such that there are 7 days in a week. This one is a statement because we can actually confirm if there are 7 days in a week. So this statement can be either true or false. You can also have P is a symbol statement, which is, so P is a symbol statement. Then we can also have R such that 3 plus 2 is equal to 6. This one is also a statement, and it's a symbol statement. You cannot break this one down. 3 plus 2 is equal to 6. It have got a truth value of what? Of false, because 3 plus 2 is actually 5. Just like that. So this one is just these are more examples which shows that is it a proposition or not? Is it a proposition or is it a statement or not? Grass is green. Grass is green. Is this a proposition? Just want to hear from you guys. This is a proposition, grass is green.
Yes, it's a proposition.
Why?
Because it's true, or is it true or false?
Okay, what about others? What you're thinking?
I think it's a proposition because it can be true, it can be false, and this one is true.
Okay, what about others? Grass is green. Is it a statement? Is it a proposition? Grass is green.
Sorry, I think you need to prove that the grass is green. Maybe so it's not a proposition.
I think
Okay,
it's a statement.
the thing is we have an unknown variable here. So we cannot take this one as a cannot take this one as a proposition. We are saying grass is green. Which grass that we are saying is green? So that we can confirm is it true or false. So this grass that we are referring to, we don't know which grass which you are referring to. This one cannot stand as a statement or as a proposition. Unless if you have the grass and you say this grass is what? Is green. Then you can say no. It's not actually that grass is not green, right? But we do not have the actual grass here that we are talking about. So we cannot say it's true. The statement is true or false. It's not all the grass which are green. Some of them are not green. But here, which grass are we referring to? It's just the same if I say 4x plus 2 is equal to 7. Can we say that one is a statement? Because we do not know the value of x. So it's not actually a proposition or it's not a statement. So this one is not a statement. So it's not a statement. And then 4 plus 2 is equal to 6. This one is a statement. Then 4 plus 2, 4 plus 2 is equal to 7. This one is also a statement. Then there are 4 fingers in a hand. Propositions. There are 4 fingers in a hand. This one, we know that a normal hand have got what? 5 fingers. A normal hand have got what? 5 fingers, right? And then if you say there are 4 fingers in a hand, then that one, you know that it's what? It's false. You know that it's false. If you are saying close the door, it's not a proposition. If you are saying x is greater than 2, this one, it's not a proposition. Why? Because we do not know the value of x. So we cannot say x is greater than 2 unless if we know the value of x. So whenever we substitute the value of x, this one we can now become, can now become a statement. He is very rich. This one, it's not a proposition again because we are saying he, but whom are we referring to? So this one, it's not a proposition as well. This one, these are more examples. X plus 2 is positive. It's not a statement. May I come in? It's not a statement because its truth value is neither true nor false. Logic is interesting. This one is a statement because if you say logic is interesting, you can now say, is it true or false? It is hot today. We can always actually look at the temperature and actually ascertain if it is true or not. -1 is greater than 0. It's a statement because we can actually look at it and say, this one is what? It's false because -1 is not greater than what? It's not greater than 0. But this one, x plus y, is not a what? It's not a statement because x and y, you do not know the values of x and y. So we cannot claim that it is equal to 12. So it is not actually a statement because we do not have its truth value as true or false. We cannot make it true or false there. Now let's talk about a compound statement. A compound statement or a composite statement is a statement which is comprised of simple statements and logical operations which are connectives, call them connectives. So in other words, when I say a compound statement, we now have maybe more than one simple statement. So a compound statement is now a statement that we can break down into singular ones or into simple statements. So we use connectives to join, or we use logical operations to join these simple statements to make what we call the compound statements. So a compound statement is denoted by use of letters P, Q, and R. Look at that. If it is a compound statement, we are now using the capital letters P, Q, and R. So this one is just an example. There are several days in a week and 12 months in a year. This is a compound statement which comprises of this statement and this statement, and we are using the logical or the logical operation and operation. This one. So there are 7 days in a week. That's the first statement, and you are joining it using the AND operation with this statement. There are 12 months in a year. Then the grass is green or it is hot today. You are joining the two using what? Using the OR operator. Using the OR operator. The operator is OR. If it is not raining, then I will go outside and eat my lunch. If it is not raining, if it is not raining, then I will go outside and eat my lunch. If you look at this one, it is raining is the first statement. I will go outside is the second statement. I will eat my lunch is the third statement. Then there is the negation of P. Where's the negation of P? All right. Then this one, if it is not raining, is now the negation of P. We are saying it is rain. Yeah, okay. So this one, if it is not raining, it's a negation of what? Of P, of the statement, it is raining. So we are starting with the negation of P. We call it the negation. Like we are flipping the statement. It was saying it is raining. Then we are saying if it is not raining, so this not is the negation of the what? Of the statement. So you're saying if it is not raining, then I will go outside. So in other words, this statement implies this one and eat my lunch there. So that's how you connect the simple statements to make a compound statement. Determine which of the following are simple statements and which are not. For those which are not, identify the simple statements used. For this one, 2 plus 3 is equal to 5. This one is just a simple statement, this one. It is hot and sun outside. If you look at this one, it is hot is the first statement, sun outside is the second statement. So this one is a compound statement. It's not a simple statement. And we are using the AND operation to join the two. And then this one, it's a simple statement. 2 plus 3 is not equal to 6. It's a simple statement. This one is not a statement at all. This one is not a statement at all because we do not have the values of X. If I study hard, then I'll pass my exam. This one, it's a statement, but it's not a simple statement. It's a compound statement. And we are using if then. We are using if then relationship. If then. We call it the implication. We call it the implication, which means if you study hard, implies that you are going to pass. This one, if this one, then this one. It's an implication. Okay. So logical operations or connectives. Let's talk about these connectives, which you are saying the what? The logical operations. So there is the negation. The negation, which means not the not operational or the not get, if you know the logic case, the not operation. And it is normally represented by this symbol, the negation, or we can just write this one, negation of P. Can do the same. Yeah, it's just the same. You can use that symbol as well. Then there is the conjunction, which is the end operation. The conjunction, which is the end of the end operation, which is actually represented by this symbol, which is actually looking upside this one. And then there is the disjunction or the OR operation, which uses this symbol. This is our OR. And then there's the conditional, this one, the conditional, which is if then, which was being used here. If I start hard, then I will pass my exam. And then we use this arrow. We use this arrow to represent this relationship. So you're behaving if A, then B. Then there is the biconditional, which is the if and only if, where the left side implies the right side and the right side also implies the left side. So if and only if and only if statement, which is a biconditional statement. So these are all the operations that we will be using in propositional logic on our compound statements, on coming up with compound statements. For example, we have P and Q. Harare is the capital city of Zimbabwe. And we have got the simple statement Q, which says 18 is divisible by 3. So if we say P and Q, which is the conjunction P and Q, we are saying, remember P is Harare is the capital city of Zimbabwe. So we'll be saying Harare is the capital city of Zimbabwe, and which is this symbol now. And 18 is divisible by 3, just like that. If it is an OR or a disjunction operator, we are saying P or Q. So we are saying Harare is the capital city of Zimbabwe, or 18 is divisible by 3. And then if it is the negation of P, we are saying it is not the case that Harare is the capital city of Zimbabwe, or we are simply Harare is not. We are simply saying Harare is not the capital of what? Of Zimbabwe. Harare is not the capital of Zimbabwe. Just like that. That's the negation. That's the negation. So the negation is just like the opposite of that simple statement. Then this one, we are given also these statements. Let P be it is hot and Q it is sun. So these are these two simple statements, and then you are having the sentence and its equivalent symbolic form. So sometimes you might be given this symbolic form and then you'll be asked to write this, or you'll be given this one and then asked to give the symbolic form of these compound statements, just like that. So if you are saying it is not hot, we are negating this P. We are saying it is hot. So the negation of P is the one that we have here. So the symbolic form is the negation of P. And then if we say it is hot and sun, if it is hot and sun, in other words, we are saying P and Q. That's why you have this P and Q. It is hot or sun. So we are saying it is hot, which is P, or sun, which is Q. So we are using this P or Q. It is not hot, but sun. It is not hot, but sun. In other words, it is not hot and it is sun. If you read it well. So you are negating it is hot, which is P, and it is sun, which is Q. That's why you have the negation of P and Q. And then we have the next statement, which says it is neither hot nor sun. It is neither hot nor sun. In other words, it is not hot and it is not sun. So you are negating P and you are negating Q and you are using an and to join them. That's why I've got the negation of P and the negation of Q. So you might be given this and asked to write the sentence, or given the sentences and asked to give its equivalent symbolic form. Do I have questions here or some contributions? Okay, if I do not have questions and contributions, I'm sure it's very clear. I'm sure it's very clear. Okay, so let's look at this practice. Let's look at this practice. Let H be equal to done is health, then W done is wealth, then S done is wise. And then translate the compound statements to symbolic form. Done is health and wealth, but not wise. If you look at this one, we've got three statements. So done is health, which means you are looking at H, and which means you are joining it with this one, done is wealth and is wealth, which means we have H and W, but not wise, which means and the negation of what? Of S, the negation of S. And then we've got this one, which says done is not wealth, which means we are starting with the negation of what? Of W, but he is health, which means we are having an end of what? H and wise. So this one is what? Then it's wise is what? It's S. So that's why you have got the negation of W and H and S. Done is neither health, wealth, nor wise. Then we are just negating everything there. Just negating everything. And we are using and operator. Do I have questions here? Okay. What about this one? Let M be equal to Alex is good in mathematics, and C Alex is a computer science student. Translate the following statement forms into plain English. Negation of C. What's the negation of C there? Just want to see if you are following. What's the negation of C?
So not.
Come again.
It's not. Alex is not a computer science student.
Okay. What else? What else? How can we else rephrase this one? I'm sure we can always have. It's correct, but I'm sure we can always have many sentences there. Now, want English doctors here. Alex is not a computer science student. What else? Okay, it's fine. You can also say it is not the case that Alex is a computer science student. This is still acceptable there. What about C or M? C or M? What about C or M? Colin, can you say something? Colin M, I don't know. It's Colin. It's Colin M. Colin Mushamba.
Okay. Okay. It's Alex is a computer science student, or Alex is good in maths.
Yeah, which is good as well. What about M and the negation of C? What about M and the negation of C? Someone to contribute? Just want to see if you're on the same page. Pamela, I've got Pamela. Pamela Chiwobo.
Alex is good in maths, but not a computer science student.
Which is very nice, but you are always quiet. I don't know what's happening, you guys. And I'm asking for contributions. No one is raising a hand, but you have the answers. Okay, anyway, a convenient method for analyzing a compound statement is to make a truth table for it. Maybe this is what we are going to discuss next. Let's talk about the truth tables. The truth tables. So a statement P can hold one of two truth values, which is true or what, or false. A statement P can hold one of two truth values, true or false. Remember, we've said a statement can be said it's a statement whenever it have got either true or false as its truth values, and it cannot be both. So that's what we are saying here. A statement P can hold one of two truth values, which is true or false. These are denoted by T and F respectively. Some books may use 1 for true and 0 for false, but here let's use a T and F. It's good as that. But if you find some books which you'll be using 1 and 0, I'm sure you now know what to do there. So when determining the truth value of a compound statement, all possible combinations of the truth values of the statements comprising it must be considered. This is done systematically by the use of truth tables. Therefore, a truth table specifies the truth value of a compound proposition for all possible truth values of its constituent propositions. So in other words, whenever you have a compound statement, you can use a truth table to find all its truth value. Then how do you construct a truth table? How do you construct a truth table? I'm sure you need to pay a special attention here if you are not yet able to construct a truth table. Because surely your exam, I'm sure you will be going to be asked about these truth tables. So to construct a truth table, assign each statement a column. If you want to construct a truth table, assign each statement a column. So you have a compound statement. So break that compound statement into simpler statement and then assign each and every statement a column. The number of rows in the table is determined by the number of statements. And for any statements, you always have 2 to the power n rows. So the number of statements will determine the number of rows that you are going to have. If you have 3 rows, you are going to have 2 to the power 3, which is going to be 8 rows. If you have 3 statements, just like that. So systematically assign truth values to each of the statements beginning in the first column. So normally here we use what we call the half rule. You start, maybe if you have got 8 columns, if you have got 8 rows, you start with maybe true, which are 4 T's and then followed by 4 false. And then on the next, you do the half of the first truth values that you have on the first column. So it will be true, maybe false, true, false. And then what the next is true, false. So we use what we call the half rule. I'll just demonstrate. Once all possible truth values for the simple statements are inserted, determine the truth values of the compound statements following the rules for the operations. Okay, so let's talk about these negations on a truth table. On how do they look like? So if P is a statement, the negation of P is not P, or it is not the case that P and is denoted by what? The negation of P. So how do you draw the truth table of this one? The first thing, remember, you have one statement. So whenever you have one statement, it's 2 to the power 1. So you always have 2 rows. That's why you have what? 2 rows. And then make sure that you assign each statement a column. That's why you have this statement P here as a column here, the column for P. And then the negation of P, this one's the result that you want. So you're going to give it also a column because this one's going to be the result. And then on the way that you are going to assign the truth values first on the statements here, on the statements, we used what we call the half rule. Since we have got actually 2 rows, so you are going to start with a true, then false. If you are going to start with the false, you just say false, true. It's still correct. You can do that. You can start by either using false and then you put the truth. But let's just do it this way. And then now we are saying the negation of P. So the negation of true is what? Is false, because we are just doing the opposite way. The negation of false is what is true. That's why we have these values. That's why we have got these values. We are applying this operation to this value, and then we get this. Applying the negation of P here, and then we get this. So this one is just a column of what? Of results. Let's look at the conjunction end. So we are looking at all those operations and look on how do they affect the input. So we're going to do both the and, the or, maybe the if, then, and then the if and only if, which is the biconditional. So the conjunction end operation is simple, the end operation. So if P and Q are statements, then the conjunction of P and Q is P and Q. Remember, we have two statements, right? Whenever you have two statements, we are saying 2 to the power 2, which is going to be 4. So we are going to have 4 rows. That's why we have this 1, 2, 3, 4 rows. And then assign each statement a column. That's why we have P and Q. And then remember, you want this compound statement P and Q. So we also assign this compound statement a column P and Q. And then the next thing is to assign these truth values here on the simple statement. How do you do so? That's when I said you use a half rule. Like here at first, we have got 4 rows, then half of that is what? Is true. So you start with these 2 truths. So true, true, and then followed by false, false. After that, you do the half of this one. Now, since we've got only 2 rows with the true, true, then half of that it's 1. So true, then false, then true, then false. So it will be true, false, true, false, true, false, just going down, just like that. And then we just want to start. This operation P and Q. How does it behave? How does it behave using a truth table? So whenever you are using this operation, true and true. So whenever you have got a statement with a truth value and actually joined with a statement the truth value, you always got a statement which is true. Then if it is true and false, we are just going to have something which is false. You are joining something which is true and something which is false. What you are going to get is corrupt, is false. It's just the same. False and true is false. False and false is always false. If you are joining something which is false with something which is false, you are going to get a what? A false. Just look at how it is when you are implementing maybe an if statement. Maybe you have a compound statement. I'm sure maybe you are saying if A is less than B and B is greater than maybe 20 there. If it is an and, if one statement result to false, then everything is what? Is false. It's just like how it operates there. That's the end operation. So here we are saying it is only true whenever both P and Q are true. Whenever both P and Q are true, that's when this end operation gives us the truth value. So it is true when and only when both P and Q are what? Are true. So if either P or Q is false, or if both are false, P and Q is also what? Is also false. And then here's the truth table to claim that. So if you are being asked to draw a truth table for P and Q operation, that's what you do there. That's what you do there. I don't know if I've got some questions or some contributions on this one. Do I have some questions? Those who can say I need much more explanation. Okay. If there are no hands, I'm sure everyone is fine. Pamela, do you want to say something? Okay.
I wanted to ask if it's the same with Boolean, the end, or in Boolean algebra.
The Boolean algebra, the end operator there is just the same.
It's just the same. Yeah,
Yes,
I've noticed that.
in terms of computation, it's just the same.
Okay, thank you, sir.
Okay. Then let's look at the disjunction or the disjunction or. So if P and Q are statements, then the disjunction of P and Q is P or Q and is denoted as P or Q is denoted as this one. It is true when at least one of P or Q is true and is false only when both P and Q are false. So for the or the disjunction operator, once if one of the two is true, then P or Q is what is true, because we are using an or. So we just if one of them is true, then we accept it, just like that. So we have what? We have two statements. So 2 to the power 2, you have got 4 rows, and then the half rule. First you've got 4 rows, so it's true, true, then false, false. And then this one half of this, so it's true, false, true, false, true, false, just like that. And then we are using or true is true, true or false is true because we have one value as true. False or true, it's what? It's true again. Then false or false, it's what? It's false, because we just need one of the input to be true for this one to be also what? To be true. So it is only false when both of P and Q are false, just like that. That's the or. Then there is what you call the exclusive or. The exclusive or is just the exclusive disjunction. I think it's as good as the one that we say less than or equal to. But now we are excluding the equal. So it's the exclusive disjunction or the exclusive or, which uses this symbol. So whenever it is true, true, it will become false. Because we are no longer using, maybe let's take a case of less than or equal to or greater than or equal to. We are now excluding the boundaries. We do not this equal part. We do not need this equal part. So whenever it is true, true, it will be false. It will be only true because we are using this one as an or when either of one of them is true or when they have different values. If it is false, false, then it is also a what? It will give you a false. So take note that it is only true whenever one of the input is true. Just like that. So when two simple propositions are combined using or, context will provide the clue as to whether the inclusive or exclusive sense is intended. Tomorrow I will go swimming or play football. Seems to suggest that I will not do both and therefore becomes exclusive or. There's no way you can be swim at the same time playing football. In other words, you are going to do one of these things at a time. So it now becomes an exclusive or. Applicants for this post must be over 25 or have at least 3 years relevant experience. Suggests that applicants who satisfy both criteria will be considered. Therefore, or becomes inclusive or. It's now become inclusive or. You can have both of these, or you can be over 25 at the same time have at least 3 years of experience. Then where context does not resolve the ambiguity surrounding the word or, the intended sense can be made clear by affixing or both to indicate an inclusive reading, or by affixing but not both to make clear that the exclusive sense is actually in is taken into consideration. Where there is no clue as to which interpretation is intended and the context does not make this clear, then or is conventionally taken in its inclusive sense. So if it is not mentioned that you are including both or but not both, or the question itself or the statements itself are not revealing that, then it is the inclusive or. Then let's talk about the if then condition or the conditional, the if then or the conditional operation. And we normally call it implies statements. So also known as what? As the implication. Consider the statement, if you earn an A in math, then I will buy you a computer. That's the implication. The statement is if you earn an A in what? In mathematics. I will buy you a computer is the second statement. And then we are using if then or the implication if then or the implication. So there is now a condition. Once you meet that condition, and then you can enjoy the benefit or something is going to happen. So this statement is made up of two simpler statements, P, which is you earn an A in math and I will buy you a computer. So the original statement is then saying, if P is true, then Q is true. The original statement is then saying if P is true, then Q is what? Is true. Or more simply, if P then Q. In short, we can also phrase this as P implies Q. In other words, we say P implies Q. If P is true, then Q is true, just like that. And we write it as P implies Q using this arrow. I'm sure I've actually explained it earlier. So if P and Q are statement variables, the condition of P of Q by P is if P then Q, or P implies Q and is denoted by P implies Q. It is only false when P is true and the Q is false. That's when it is only false. We cannot have the truth which will be implying false. Hakuna zvakadaro. If you earn an A in math, then I will buy you a computer. Then wobva wafoira. Atuto wobva wapasa tobva tatadza kutengere computer. That one. Hakuna zvakadaro handiti. We've promised that and we'll do that. That's the rule. So it is only false when P is true and Q is false. Otherwise, it is always true. So the arrow is the conditional operator, and in P implies Q statement, it is called hypothesis or antecedent, and the Q is called the conclusion or the consequent. So this one is the hypothesis and this one is the consequence. So the truth table will be just looking the same because we have these two statements, and after this you draw your truth table and you place your truth values on these two columns, and then you find these values. So P implies Q, we are saying true implies true. Yes, it will give you the true value. Like if you earn an A, you are going to buy your computer. And then if you earn an A and fail to buy you a computer, it's false. You are not going to do that. You are not going to have a scenario where someone is going to have an A and not actually have his or her computer being bought. In other words, hatina chokwadi chinotifamba nyepo handiti. A truth cannot imply false. A truth cannot imply false. So here it will give you a false. Then false implies true. Yes, we can accept that as what is a true. That someone didn't pass but actually got a computer. Also, false can imply false. False can imply false, and then we can take that one as a what? As a true. False can imply false. That's what is true. So it is only false when the truth imply false, when the truth imply false. Just like that. Other ways of expressing implications, the implication P implies Q could be expressed in many alternative ways. If P, then Q, or we can say not P unless Q. Not P unless Q is just the same as P implies Q. P implies Q, Q follows from P. Can be given something like this. Q follows from P. It is still the implication. If PQ is just the what? The same implication. Q if P is also the implication. P only if Q. P is sufficient for Q. Q whenever P. Q is necessary for P. All these statements, they are just revealing the P implies Q. So it's just the terminology that can be used there, that can be used. More about conditional statement. Given the conditional proposition, P implies Q, we define the following: the converse and the inverse and the contrapositive. You need to take note of this. There's what we call the converse of the implication or of the conditional statement, and we have what we call the inverse, and we also have what we call the contrapositive. We have what we call the contrapositive. So what we call the converse of P implies Q is just the opposite. This is when we have Q, which will be implying P. That's what we call the converse. So you might be asked to give the converse of a statement. Maybe in words, you are given a statement in words, and then you'll be asked to give the converse of a statement. So whenever you have P implies Q, the converse of that statement is Q implies P, the opposite one. Then the inverse of P implies Q is just the negation of P implies the negation of Q. So you just negate both P and Q. That's the inverse of P implies Q. Then the contrapositive of P implies Q, you need to interchange. The first thing is going to, in other words, the first thing is going to have Q implies P, and then you negate. Or the contrapositive is just the negation of the converse. You negate this Q and then this P. Then it will become the contrapositive of P implies Q. So you'll be having the negation of Q implies the negation of P. Do I have the questions or contributions on the converse and the inverse and the contrapositive of a conditional statement? Okay, it seems that there are no hands. It's fine. Let's look at this truth table, which shows the converse, the inverse, as well as the contrapositive. So this was the contrapositive, this one, converse, the inverse, and then these are the what? These are the statements. So as well as only a number of statements, manga, and if you just look at all the compound statements that we have, they only have P and Q. So in other words, you only have two statements. Just R or whatever statement, we are just having two simple statements, which is P and Q. So the first thing is to have these columns for P and Q, and then we're going to have the P implies Q, and then from this P implies Q, we are going to work out the converse, the inverse, as well as the contrapositive statement. So true, true, false, false, true, false, true, false. These are things that you be actually first start with, and then we fill in all these values. So I'm sure here true implies true, we get a true. True implies false, we get a false. False implies true, we get a true. And then false implies false, you're going to get a true there. And then after that, you're going to get a true. So that's what we have on P implies Q. What about on Q implies P? In other words, we are now saying Q implies P. So I say true implies true, yes. False implies true, yes. And then true implies false, it's now false. And then false implies false, it's what? It's true, just like that. That's how you do it. And then when the negation of P implies the negation of Q. So I'm sure you need to now have a separate, maybe a column for the negation of what? Of P, and then another column for the negation of Q, so that it will become easier for you to do this. Where you just say the negation, you just go to the column of the negation of P, and then you say implies the negation of Q. But anyway, you can do it directly by first negating true, you have a false, and then you negate this one, you have a false. Then you say false implies false, you get a true. Then you come here, you negate this and negate this. Then you have a false implies true, because here you negate this one. So false implies true to become true. Then you have true implies false, it will become false. And then you have a true implies true, which will become true. And then here you are doing the vice versa. And then you negate, so you say Q to P, but you need to negate all these values so that you can get this value. So these are the truth values for the converse, the contrapositive, as well as the inverse. That's what you have there. So state the converse, inverse, and the contrapositive of the proposition. If Jack plays his guitar, then Sarah will sing. State the converse, the inverse, and the contrapositive of the proposition. If it's not Sunday, then the supermarket is open until midnight. Let's start with the converse statement of the first implication, which says if Jack plays his guitar, then Sarah will sing. Can I have someone to give me the answer here? If Jack plays guitar, then Sarah will sing. Someone to contribute. Someone to contribute. Can I have someone to contribute?
Sarah will sing if Jack plays his guitar.
Sarah will what?
Will sing if Jack plays his guitar.
That's the converse.
Yes.
Is it the correct way of saying it? Remember, we need the if then there, because it's an implication. Yes, there is a hand by Mu. I don't know. It's MU on your username, so I don't know, but I'm sure you can unmute yourself and contribute. Can I?
Taking if Jack plays the guitar for P and then Sarah will sing for Q. I think the first statement will be P, and then if it's true, then Sarah will sing, which is Q. It's only true when it's P and Q. And then if it's the inverse, if Jack doesn't play the guitar, Sarah will not sing.
No, I just want the converse. I just want the converse. Just want the converse. Okay, at first, the converse. What's the converse of P implies Q? You are saying P implies Q. What's the converse of that one? Okay, Monica, you can come in. You can say something there if you want.
The converse of P implies Q is Q implies P.
Right, is what is Q implies P. So you are just doing the vice versa there. So you were saying if Jack plays guitar, then Sarah will sing. So if you look at this one, we've got two statements. Sarah will sing and Jack plays guitar. So you need to find and then this one is P, and then this one is what is Q. So we are saying P implies Q. And then when you're saying the converse, you are now you have Q implies P. Q implies P, which means if Sarah will sing, then Jake plays his guitar. Remember, Q implies P. We are using the if, the conditional statement. So your statement is not if then. Then it means it's no longer a what? It's no longer an implication or a condition. Unless if you raise it using these statements. Not P unless Q follows this and whatever. If you are using these keywords. Sarah whenever, or Sarah will sing whenever what's the name there? Whenever Jake plays his guitar. It's still acceptable. Just like that. Okay. What about the inverse? The inverse of this P implies Q. What about the inverse? Let's hear from others. What about the inverse?
I think inverse is the negation of converse.
The inverse is the negation of what?
Converse.
Of the converse. Exactly, that's it. The inverse is the negation of the converse. So what could be the statement in English? The inverse, you said the inverse is the negation of what? You've said the
Inverse is the negation of converse.
Is it true?
No, say I think the inverse is
the negation of the
P, yeah, of the statement. P implies Q. The negation of P implies the negation of Q.
Exactly, that's it. The inverse, you are just negating P implies Q. That's the inverse. You are just negating P implies Q. So in other words, we are saying just negate this statement. If Jake plays his guitar, then Sarah will sing. So what will be the answer there? What will be the answer there? I'm not seeing any hints.
Let me try.
Yes.
If Jack will not play his guitar, then Sarah will not sing.
Okay. It's correct. It's correct. It's correct that way. If Jack doesn't play his guitar, then Sarah won't sing. If Jack doesn't play his guitar, then Sarah won't sing. What about the contrapositive? What about the contrapositive? Contrapositive. What about the contrapositive? I do not have any hands.
That's the negation of the converse.
Exactly. The contrapositive is now the negation of the what? Of the converse. And then what could be the answer in words here? Joseph. Is it Joseph? I'm sure I saw a hint and then the hint just got disappeared.
If Sarah doesn't sing, Jackie will not play his guitar.
Exactly. So if Sarah won't sing, then Jack doesn't play his guitar. That's the contrapositive statement there. That's contrapositive statement there. Thank you for that. And then if it's not Sunday, then the supermarket is open until midnight. That one, you do it as an exercise. And then let's look at the inverse of conditional statements. Inverse of conditional statements. Like on the truth table, how does it look like? So the inverse of the conditional statement, P implies Q, is negation of P implies the negation of Q. Remember, we have only two statements, so we are going to have 4 rows, and then half rule, true, true, false, false, and then true, false, true, false. And then from there, we are going to have this implication. And then if you look at this, you want to find the inverse. And then the inverse negation of P implies negation of Q. That's why we are having this negation of P and negation of Q, so that it will be easier for you to do the implication by just looking at this value rather than first flip the value here and then do the implication. That's why you have this extra 2 columns. And then the result is this one, which is our inverse statement. So from here, I'm sure everyone can come up with these values. True implies true, yes. True implies false, false. True implies false implies true, which will give you a true. Then this one give you a true. Then the negation, you are just negating all these values. So whenever you have a true, you're going to put a false. That's why a false, false, and then true, true. And then on here, you're just negating these values again. Whenever you have a true, you're going to put a false. That's why a false, true, false, true. And then we are saying the negation of P implies negation of Q. So the negation of P implies the negation of Q. So false implies false. That's why you have this value. True, false implies true. You have a true. True implies false. You have a false. And then true implies true. You have a what? You have a true. You have a true. So the inverse of the conditional statement P implies Q is negation of P implies negation of Q. A conditional and its inverse are not equivalent. This could be seen from the truth table. So we are saying the inverse and the original conditional statement, they are not equal. They are not equal. Since you see here, we've got a false, but here we've got a true. Here we've got a true, and here we've got a false. So they are not what? They are not equal. Then there is the biconditional, which is the if and only if statement. So if P and Q are statement variables, the biconditional of P and Q is P if and only if Q, and is denoted by this double arrow, which is the forward and backward arrow. P implies Q. So we just say P and P, if P and only if Q. And it can be abbreviated as IFF, is if and only if. So the double-headed arrow, this one is the biconditional operator. So normally, if you look at this one, it is only false whenever you have different input values. Otherwise, it is always true. So true, true, it will give you true. False, false, it will give you true. But whenever you have a true and a false, false and a true, you are going to have a result as false. That's the if and only if biconditional or the biconditional operator. So is there any contribution that needs to be made? I'm hearing some noise from some certain line. Sure, it's Nyasha, Nyasha, man. Shona, do you want to say something? Okay, let me just mute you. Okay, so alternative word for P, for if and only if and only if can be P if and only if Q, or PIFQ. P implies and is implied by Q, or P is equivalent to Q, or P is a necessary and sufficient condition for Q. So those are some alternative wording that can be used. Then let's look at the order of operation for logic conditions. Evaluate negations first, and then evaluate the or and the end operator. When both are present, parentheses may be needed. Otherwise, work left to right. It's like if you want to evaluate them, then evaluate the implication, and then lastly, the biconditional. When both are present, parentheses may be needed as well. Otherwise, work from left to right. Note that use of parentheses will determine order of operations which override the above order. In other words, whenever there are parentheses, you need to start with those which are in parentheses. So in summary, we've learned what is a statement, how a compound statement can be formed. From what is a statement, I'm sure you've said a statement, it's just a sentence with a truth value which is either true or false, and how a compound statement is formed. I'm sure they've shown you that you can use the logical connectives to form the compound statements. Also, we've got the logical connectives or operations, the negation, conjunction, disjunction, the implications. Also, we have actually shown you how to construct a truth table, Now let's talk about what we call a tautology. So a tautology is a statement from that is always, so a tautology is a statement form that is always true regardless of the truth values of the statement variables. A tautology is represented by the symbol T. So we are saying a tautology is a statement which always truth values, regardless, truth values is true, regardless of the values in its statement variables. Like if you look at this truth table, you can say P or the negation of P is always a tautology, since we always have only truths in its value or in this critical row. This is the row that you are looking at, the critical column, sorry. So the statement of P or the negation of P is a tautology because all the values here are true. Then there's what we call a contradiction. So a contradiction is a statement form that is always false regardless of the truth values of the statement variable. So a contradiction will always have false here. That's what we call a contradiction, regardless of the values that we have here. So this is an example of a contradiction. We have some false in this critical column. So the remarks, most statements are neither tautologies nor contradictions. A proposition that is neither a tautology nor a contradiction is called a contingent. There's what we call a contingent. So it's something which is not a tautology nor a contradiction. So in other words, it was some mixture of values here on this. It will have some false and truths or something like that. That's what we call a what? That's what we call a contingent. So the negation of a tautology is a contradiction, and vice versa. The negation of a tautology is a contradiction. So if you negate a tautology, you're going to get a contradiction. If you negate a contradiction, you're just going to get a tautology. I'm sure it's very simple and straightforward. Negating this whole thing, you get true, which will give you a tautology. And negating this one, will give you false, which is going to give you a contradiction. And then let's talk about the logical equivalence. The logical equivalence, what else, what we need to talk about? Okay, I'm sure you are reaching the end of this one. Okay, so the logical equivalence, two compound propositions are called logical equivalent if and only if they have the same truth values, no matter what truth values their constituent proposition they have. For instance, P implies Q and negation of P or Q are logically equivalent, and we write P implies Q is logically equivalent to negation of P implies Q. Note that if two propositions P and Q are logically equivalent, then P implies Q, P and if and only if Q is a tautology. Okay, let's just look at this one. When you say they are logically equivalent, we have P implies Q, and just wait a little bit. Okay, so when you're being asked to show that P implies Q is logically equivalent to negation of P or Q, you can use a truth table. And remember, we only have two statements. That's why we have these 1, 2, 3, 4 rows, and then we use the alpha of rule to construct the truth table. But before we show this one, do you guys have the challenges on construct truth table? Someone who can say, I cannot construct a truth table. It's good to say it. It's good to say it. Okay, it's okay. I'm sure you are good with that. And I'm no longer assuming, because you have said you are good at it. So now, since we want to use the negation of P, so just do the negation of P. By negating this one, you are going to have a false, then here a false, and then negating false, you're going to get a true, negating a false, you're going to get a true value there. And then you do the implication. You know, when you are saying true implies true is going to give you a true, true implies false is going to give you a false. Excuse me, but false implies true is going to give you a true, false implies true is going to give you a true. So now you do the implication. You now do the negation of P or Q. You know, the OR operator, the OR operator. So you are now looking at this one and this one, these two. So you are saying false or true, it will give you true, and then false or false, it will give you false. Then true or true, it will give you true, and true or false, it will give you true. Then you look at these two. You look at these two. When you have a true here, you have a true. When you have a false, you have a false. When you have a true, you have a true. When you have a true, you have a true. So we can say these ones are logically equivalent, just like that. Then this was just this section. You can look at it later. You can look at it later when you're doing maybe discrete mathematics there. But it's also good to just have a look at it, just have a look at it. But I'm not going to dive into all these things. I'm not going to dive into these laws of logic. I'm not going to dive into these laws of logic. You can have a look at them later. Yeah. Okay. Do I have questions? Do I have questions? Do I have questions? Before we close this topic, do I have contributions? Before I close this topic, okay, so if I do not have questions, let me unshare my slide. Then we will be left with the predicates and the logic. Predicates logic and the Boolean algebra. Predicates logic and the Boolean algebra. And I will trust you that you can read the Boolean algebra. I will trust you that you can do that. There isn't much of the comment there. Maybe it's a 14 slides there. I'm sure you can do this one. Then on the issue of predicates, I will share you a video. I have done a video on this one. I will just share that video. You watch that. If you have some questions, you ask. I'm sure that's the best way that I can do that. I have a video that I've actually done using the slide. I'm not going to repeat that. The video is there on the channel. Maybe what I can do, maybe is to help you to spot that video. I'm sure it's there. And then if you have something to ask, you will come and ask. In other words, I'll close this module. I'll close this module now. So here's the time for you to ask some questions regarding this module. And I'm not going to record this section. Okay, let's talk some areas we are facing the challenges.